My name is Laura Gomez-Rey, and this is my Physics 2212 Lab 4 for circuits. Alright, so the purpose of this lab is to predict and model the behavior of circuits and how the current and potential differences are affected by the components such as capacitors and resistors. And most of the key concepts that we're going to need for this experiment are going to be Kirchhoff's rules, which include the loop and node law, which basically means like I1 is equal to I2 plus I3, meaning that like the current is I1 and then it gets split off into two other currents or two other wires, and the current of those two wires added together has to equal the current of the first wire that before it was split up. And then we have Ohm laws, which is V is equal to IR, which is just for one wire. And then we need the circuits in series and parallel, which we need to know, and we need to know how RC circuits work, which is it's a circuit which is a combination of having resistors and capacitors together. Okay, for the actual experiment, for model and prediction, the model we used is the PHYS simulation, and I predicted that the currents will be I1 and I2 will be the same. And for assumptions, I assumed that resistance in the wire is negligible and resistance is negligible within the ammeters. And with the initial conditions, the system will be circuit and the surroundings will be everything else, and the initial conditions will change depending on the experiment. So for experiment 1, the initial conditions were that the presence of the two 1.5 V batteries that has a total of 3 voltage EMF, and then 2 resistors in the series and a resistance of 47 ohms and 100 ohms with 1 ammeter before the resistors and 1 ammeter after the resistors. And my predictions were that the currents were going to be the same as a result of Kirchhoff's rules. And I1 and 2 are going to be equal to 3V divided by 147 ohms. And I1 is going to be 0.02 and I2 is 0.02 as well, with the voltage being 3 volts at I2. So for the actual experiment, the resistor and ammeter were in parallel, and actual values were 48 ohms, 102 ohms, and 0 ohms for the wire and ammeter because, again, using the loop rule, everything has to be equal to 0 at the end. So these are all, you can see on the right, all the smaller segments calculated, and then we can see that after VNet has to be equal to 0, and it does after all of them being calculated. And this is the graph of each individual segment and how it leads back to 0. And then current when ammeter is in parallel is 0.06 amps. Alright, and then for experiment 2, the initial conditions were the 9-volt battery, 10 ohm and 20 ohm light bulbs acting as resistors, and 200 mF capacitors. So when I timed the charge and discharge times for the 10 ohm resistor, I got 4.16 seconds, and for the 20 ohm resistor, I got 8.95 seconds. And then for the charging capacitor, the voltage rises and the bulb slowly dims until the current reaches 0 amps, which is due to the loop rule. And then the discharging capacitor, while discharging, the voltage drops until the current reaches 0 while the bulb dims. And then for experiment 3, the initial conditions were that V0 is equal to 9 volts and 30 ohm light bulb acting as the resistor. And again, the capacitor is attached to the circuit. And for the calculations, we got that the slope was timed at 6.207 seconds, with the theoretical RC being 6 seconds, and between these two, the sources of error, again, could have been rounding errors on the simulation or timing errors in the actual values, which were done by me. So for what-if questions, for time, I'm just going to say the answer, and then but the question is up there. So for the first what-if question, there would be some resistance provided by the ammeter simply due to its inner material properties making its resistance greater than 0. And for the second what-if question, it only took 0.3 seconds for the capacitor to change in this simplified circuit, but the real world it would take longer due to the actual materials having some resistance not focused on this model. Thank you.